Welcome all SYPSC students. Today we can take paper first MTH 301 Calculus of several variable. Unit first function of 2 and 3 variables. Video number 4 higher order partial derivatives. I'm Mr. S.R. Gaikwad, Assistant Professor in Department of Mathematics, Arts, Commerce and Science College Java. Please subscribe my YouTube channel, Mr. S.R. Gaikwad. Today you can find higher order partial derivatives. First you can find partial order derivatives at origin. Working rule for finding fx at 0, 0, fy at 0, 0, fxy at 0, 0, and fyx at 0, 0. First, by definition of partial derivative, fx at 0, 0 equal to limit h tends to 0, f of h, 0 minus f of 0, 0 upon h. Nothing but partial derivative of function f with respect to x at point 0, 0. Second, fy equal to fy at 0, 0 equal to limit k tends to 0, f of 0, k minus f of 0, 0 upon k. This partial derivative of function f with respect to y at 0, 0. Third, fx at 0, k equal to limit h tends to 0, f of h, k minus f of 0, k upon h. Then fy at h, 0 equal to limit k tends to 0, f of h, k minus f of h, 0 upon k. Then second order derivatives, f xy at 0, 0 equal to limit k tends to 0, fx at 0, k minus fx at 0, 0 upon k, nothing but mix second order partial derivative of xy at 0, 0 and fyx at 0, 0 equal to limit h tends to 0, fy at h, 0 minus fy at 0, 0 upon h. These are the partial derivative at 0, 0, first and second order. Examples. If f of x, y equal to x into y into x square minus y square upon x square plus y square, comma, x, y not equal to 0, 0 and f of 0, 0 equal to 0. Show that f xy at 0, 0 is not equal to f yx at 0, 0. Solution. Let f of x, y equal to xy into bracket x square minus y square upon x square plus y square, comma, f of x, y not equal to 0, 0 and f of 0, 0 equal to 0. First we can find fx at 0, 0. By definition, equal to limit h tends to 0, f of h, 0 minus f of 0, 0 upon h equal to, in given function we can put x equal to h and y equal to 0, nothing but h into 0 into in bracket h square minus 0 upon h square plus 0 minus f of 0, 0, 0 upon h. But h into 0, it means whole term is 0, it means value of limit is 0. Then we can find f at 0, 0 equal to limit k tends to 0, f of 0, k minus f of 0, 0 upon k equal to limit k tends to 0. In given function, we can put x equal to 0 and y equal to k. If we put x equal to 0 and y equal to k, we get 0 into k into in bracket 0 minus k square upon 0 plus k square minus f of 0, 0 is 0. It means 0 into k, nothing but whole term is 0, and therefore here also value of limit is 0. Therefore fx at 0, 0 is 0, f at 0, 0 is 0. Then we can find fx at 0, k equal to limit h tends to 0, f of h, k minus f of 0, k upon h equal to limit h tends to 0, f of h, k, it means in given function we can put x equal to h and y equal to k. We get h into k in bracket h square minus k square upon h square plus k square minus 0 upon h. Clearly here h cancel. We get k into h square minus k square upon h square plus k square. Then as limit k tends to 0, we can put here k equal to 0. If we take here k equal to 0, we get sorry, if we can here limit h tends to 0, we can put here h equal to 0, and therefore here k into 0 minus k square upon 0 plus k square. Then here minus k square upon k square, here k square is cancelled, that is bracket term is minus 1 into k, that is value of limit is minus k. Therefore fx at 0 comma k is minus k. Then fy at h comma 0 equal to limit k tends to 0, f of h comma k minus f of h comma 0 upon k equal to limit k tends to 0. Here f of h comma k nothing but h into k into h square minus k square upon h square plus k square minus f of h comma 0 is 0. Here k cancel, remains h into h square minus k square upon h square plus k square. As limit k tends to 0, we can put here k equal to 0. We get h into h square minus 0 upon h square plus 0. Then here h square cancel, and therefore the value of limit is h. And therefore fx at 0 0 equal to 0, f at 0 0 equal to 0, fx at 0 comma k equal to minus k, fy at h comma 0 equal to h. Then we can find second order derivative. And therefore fxy at 0 0 equal to limit k tends to 0, fx at 0 comma k minus fx at 0 0 upon k equal to limit k tends to 0, fx at 0 comma k nothing but minus k minus fx at 0 0 is 0 upon k, that is minus k upon k, here k cancel, that is value of limit is minus 1. Then fyx at 0 0 equal to limit h tends to 0, fy at h comma 0 minus fy at 0 0 upon h equal to limit h tends to 0, fy at h comma 0 is h minus fy at 0 0 is 0 upon h, that is h upon h cancel, that is remains 1, that is as limit h tends to 0, value of limit is 1. Therefore fxy at 0 0 is minus 1, fyx at 0 0 is 1, and therefore clearly fxy at 0 0 is not equal to fyx at 0 0. Next example. If f of x comma y equal to x square into y square upon x square plus y square, comma x comma y not equal to 0 comma 0, and f of 0 0 equal to 0, show that fxy at 0 0 equal to fyx at 0 0. Solution: it is given function f of x comma y equal to x square into y square upon x square plus y square if x comma y not equal to 0 0, and f of 0 comma 0 equal to 0. First you can find fx at 0 0 equal to limit h tends to 0, f of h comma 0 minus f of 0 comma 0 upon h equal to limit h tends to 0. In given function, we can put x equal to h and y equal to 0. We had h square into 0 upon h square plus 0 minus f of 0 is 0 upon h. Here h square into 0, it means whole term is 0, and therefore value of limit is 0. Then fy at 0 comma 0 equal to limit k tends to 0, f of 0 comma k minus f of 0 comma 0 upon k equal to limit k tends to 0. In given function, we can put x equal to 0 and y equal to k, that is 0 into k square upon 0 plus k square minus f of 0 comma 0 is 0. It means 0 into k square, it means whole term is 0, that is as limit k tends to 0, the value of limit is again 0. It means fx is 0, fy is also 0. Then fx at 0 comma k equal to limit h tends to 0, f of h comma k minus f of 0 comma k upon h equal to limit h tends to 0, f of h comma k, we can put x equal to h, y equal to k, we get h square into k square upon h square plus k square minus, if you take x equal to 0, value of function is 0 upon h. Then here 1h cancel, here to get limit h tends to 0, h into k square upon h square plus k square. But as limit h tends to 0, we can put here h equal to 0. If you take value of h at 0, that is whole term is 0, it means value of limit is 0. Then fy at h comma 0 equal to limit k tends to 0, f of h comma k minus f of h comma 0 upon k equal to limit k tends to 0, f of h comma k nothing but h square into k square upon h square plus k square minus f of h comma 0 is 0 upon k. Then here k cancel. We get limit k tends to 0 of h square into k upon h square plus k square. As limit k tends to 0, we can put here k equal to 0. If you take k equal to 0, then clearly whole term is 0. It means value of limit is 0. And therefore, fx at 0, 0 equal to 0, fy at 0, 0 equal to 0, fx at 0, comma k equal to 0, fy at h, comma 0 equal to 0. And therefore, fxy at 0, 0 equal to limit k tends to 0, fx at 0, comma k minus fx at 0, 0 upon equal to limit k tends to 0, fx at 0, comma k is 0 minus fx at 0, 0 is also 0 upon k, and therefore clearly value of limit is 0. Then fyx at 0, 0 equal to limit h tends to 0, fy at h, comma 0 minus fy at 0, 0 upon h equal to limit h tends to 0, fy at h, comma 0 is 0, fy at 0, 0 is also 0, and therefore value of limit is 0. Therefore, fxy at 0, 0 equal to 0, fyx at 0, 0 equal to 0, and therefore fxy at 0, 0 equal to fyx at 0, 0. It means both values are equal. Next, if f of x comma y equal to x cube into y upon x square plus y square, comma x square plus y square not equal to 0, and f of 0 comma 0 equal to 0. Show that fxy at 0, 0 is not equal to fyx at 0, 0. Now this given function f of x comma y, given that f of 0 comma 0 equal to 0. First fx at 0, 0 equal to, by definition, limit h tends to 0, f of h comma 0 minus f of 0, 0 upon h. Equally limit h tends to 0. In given function, we can put x equal to h, y equal to 0. If we take y equal to 0, we get h raised to 3 into 0 upon h square plus 0 minus f of 0, 0, 0 upon h. Then h raised to 3 into 0, it means clearly this whole term is 0, and therefore value of limit is 0. Fy at 0, 0 equal to limit k tends to 0, f of 0 comma k minus f of 0, 0 upon k equal to limit k tends to 0. In given function, we can put x equal to 0 and y equal to k. If we take x equal to 0, we get 0 into k upon 0 plus k square minus f of 0 comma 0 is 0 upon k. But 0 into k, it means clearly again whole term is 0, it means value of limit is 0. Therefore fx is 0, fy is also 0. Then fx at 0 comma k equal to limit h tends to 0, f of h comma k minus f of 0 comma k upon h. Equal to limit h tends to 0, f of h comma k nothing but h raised to 3 into k upon h square plus k square minus f of 0 comma k is 0 upon h. Then clearly here h cancel. We get limit h tends to 0 of h square into k upon h square plus k square. As h tends to 0, we can put here h equal to 0. It means value of limit is 0. Then fy at h comma 0 equal to limit k tends to 0, f of h comma k minus f of h comma 0 upon k equal to limit k tends to 0, f of h comma k nothing but h raised to 3 into k upon h square plus k square minus f of h comma 0 is 0. Clearly here k cancel. We get limit k tends to 0 of h raised to 3 upon h square plus k square. As k tends to 0, we can put here k equal to 0. Get h raised to 3 upon h square. Then clearly h square cancel, and therefore value of limit is h. And therefore fx at 0, 0 equal to 0, fy at 0, 0 equal to 0, fx at 0 comma k equal to 0, and fy at h comma 0 equal to h. Then we can find second derivatives, and therefore fxy at 0, 0 equal to limit k tends to 0, fx at 0 comma k minus fx at 0, 0 upon k equal to limit k tends to 0, fx at 0 comma k is 0 minus fx at 0, 0 is 0 upon k. It means value of limit is 0. Then fyx at 0, 0 equal to limit h tends to 0, fy at h comma 0 minus fy at 0 0 upon h equal to limit h tends to 0, fy at h comma 0 is h minus fy at 0 0 is 0 upon h, then h upon h cancel here, it means clearly value of limit is 1. And therefore fxy 0 and fyx is 1, and therefore fxy at 0 0 is not equal to fyx at 0 0. Okay, next example. If f of x comma y equal to x square into tan inverse of y upon x minus y square into tan inverse of x upon y, comma x comma y not equal to 0 0, and f of 0 comma y minus f of x comma 0 equal to 0, show that fxy at 0 0 is not equal to fyx at 0 0. Solution: given function f of x comma y equal to x square into tan inverse of y upon x minus y square into tan inverse of x upon y, comma x comma y not equal to 0 comma 0, and f of 0 comma y is same as f of x comma 0 is same as 0. It means clear here, if you take x equal to 0, value of function is 0. If it y equal to 0, value of function is 0. That is clearly here, if x take x and y both are 0, again value of function is 0. Therefore fx at 0 comma 0 equal to limit h tends to 0, f of h comma 0 minus f of 0 0 upon h equal to limit h tends to 0. In given function, we can put x equal to h and y equal to 0. If we take x equal to h and y equal to 0, we get h square into tan inverse of 0 upon h minus 0 into tan inverse of h upon 0 minus f of 0 0 upon h. We know that value of tan inverse of 0 is 0. Second term is also 0. It means clearly value of limit is 0. Note that here. Tan inverse of 0 is 0. It means first term is 0. Second term is clearly 0. It means value of limit is 0. Then fy at 0 0 equal to limit k tends to 0. F of 0 comma k minus f of 0 0 upon k equal to limit k tends to 0. We can put here x equal to 0 and y equal to k. We get 0 into tan inverse of k upon 0 minus k square into tan inverse of 0 upon k minus 0. Clearly here first term is 0. In second term, tan inverse of 0 is 0, and therefore whole term is 0, and therefore value of limit is 0. Then fx at 0 comma k equal to limit h tends to 0, f of h comma k minus f of 0 comma k upon h equal to limit h tends to 0. In given function, we can put x equal to h, y equal to k. We get h square into tan inverse of k upon h minus k square into tan inverse of h upon k minus f of 0 comma k 0 upon h equal to limit h tends to 0. We can divide separately by h. If we divide by first term, at that time h cancel. Get h into tan inverse of k upon h minus second term is k square into tan inverse of h upon k upon h equal to limit h tends to 0. First term as it is h into tan inverse of k upon h. Now we can simplify this term. We can transfer one k in denominator, and therefore this term can be expressed as k into tan inverse of h upon k upon h upon k. We know that as limit h tends to 0, tan inverse of h upon k, value of this limit is 1, because limit of tan inverse of x upon x as x tends to 0 is 1. And therefore, as limit h tends to 0, if you take h equal to 0, value of first term is 0. Here k into limit of tan inverse of h upon h upon k, limit of this term is 1, and therefore clearly value of limit is minus k. Then fy at h comma 0 equal to limit k tends to 0, f of h comma k minus f of h comma 0 upon k equal to limit k tends to 0, f of h comma k nothing but h square into tan inverse of k upon h minus k square into tan inverse of h upon k minus f of h comma 0 is 0 upon k. Divide separately. Get first term, limit k tends to 0, h square into tan inverse of k upon h upon k. If we divide by second term, at that time k cancel, we get k into tan inverse of h upon k equal to limit k tends to 0. Again, we can simplify this. We can transfer 1h in denominator, and therefore h into tan inverse of k upon k upon h minus k into tan inverse of h upon k. And then as h tends to 0, limit of tan inverse of k upon k upon h. As k tends to 0, value of this limit is 1. The first term is h into 1. In second term, we can put here k equal to 0. It means limit is 0. And therefore, h into 1 minus 0, it means value of limit is h. And therefore, fx at 0, 0 equal to 0. Fy at 0, 0 equal to 0. Fx at 0, comma k equal to minus k. Fy at h, comma 0 equal to h. And therefore, fxy at 0, 0 equal to limit k tends to 0. Fx at 0, comma k minus fx at 0, 0 upon k equal to limit k tends to 0. Fx at 0, comma k is minus k minus fx at 0, 0 is 0 upon k. And here k cancel, therefore clearly value of limit is minus 1. Fy at 0, 0 equal to limit h tends to 0. Fy at h, comma 0 minus fy at 0, 0 upon h equal to limit h tends to 0. Fy at h, comma 0 is h minus fy at 0, 0 is 0 upon h. Then clearly h cancel, and therefore value of limit is 1. And therefore clearly here fxy at 0, 0 is not equal to fyx at 0, 0. Next, if u equal to tan inverse of x square into tan inverse of y upon x minus y square into tan inverse of x upon y, show that dabba square u of dabba x dabba y equal to x square minus y square upon x square plus y square. Here y nothing but here we can take u. Let u equal to x square into tan inverse of y upon x minus y square into tan inverse of x upon y. First we can find derivative of u with respect to y. To find derivative of u with respect to y, at that in first term x square is constant term. We can find derivative of tan inverse of y upon x with respect to y. We know that derivative of tan inverse x is 1 upon 1 plus x square. Derivative of tan inverse of y upon x is 1 upon 1 plus y upon x bracket square into derivative of y upon x with respect to y is 1 upon x because derivative of y is 1 minus in second term we can apply the product formula. First you can take y square constant. Derivative of tan inverse of x upon y is 1 upon 1 plus x upon y bracket square into derivative of x upon y with respect to y, in which x is constant term. Derivative of 1 upon y is minus 1 upon y square. That is minus x upon y square minus. Then we can take tan inverse of x upon y as constant into derivative of y square is twice y. Then we can simplify it. We get x square into this 1 plus y square upon x square. It means x square plus y square upon x square. Then we can simplify. We get x square upon x square plus y square into 1 upon x minus y square into. We can simplify this term. We get y square upon y square plus x square into minus x upon y square minus tan inverse of x upon y into twice equal to. Here x, clearly here x cancel. We get x cube in x cube upon x square plus y square. In second term y square cancel, minus minus plus, we get x into y square upon y square plus x square. In first term x cancel, in second term y square cancel. Last term as it is minus twice y into tan inverse of x upon y. Then from first two term we can take x upon x square plus y square as common. In first term remains x square, in second term remains y square. Last term minus 2y into tan inverse of x upon. From the first two terms, we can take x upon x square plus y square common. First term remain x square, second term remain y square. Then clearly this x square plus y square cancel, and therefore equal to x minus twice y into tan inverse of x upon y. This derivative of u with respect to y. And therefore, dabba square u of dabba x dabba y equal to dabba of dabba x in bracket dabba u of dabba y equal to dabba of dabba x in bracket dabba u of dabba y nothing but x minus twice y into tan inverse of x upon y. To find derivative of this bracket term with respect to x, in which derivative of x is 1. In second term twice y is constant term. To find derivative of tan inverse of x upon y with respect to x is 1 upon 1 plus x upon y bracket square into derivative of x upon y with respect to x is 1 upon y because the derivative of x is 1. Simplify, get 1 minus twice y into, we can simplify this term, we get y square upon x square plus y square. Then clear here, y, here y cancel, we get 1 minus 2y square upon y square plus x square. Again simplify, multiply 1 by x square plus y square, we get y square plus x square minus 2y square upon x square plus y square. Then clear here where y is cancelled, and therefore dA by square u of dA by x dA by y equal to x square minus y square upon x square plus y square, which is the required solution. Last, if you take x raised to x into y raised to y into z raised to z equal to c, show that dA by square z by dA by x dA by y equal to x into log of ex bracket raised to minus 1 at x equal to y equal to z. Solution. Given function is x raised to x into y raised to y into z raised to z equal to c. To find the root of this term, first taking log on both sides, we get log of x raised to x into y raised to y into z raised to z equal to log of c. Applying rules of logarithm, we get x into log x plus y into log y plus z into log z equal to log of c. Now to find here dA by square z by dA by x dA by y, it means clearly here z is function of x and y. You can find the root of z with respect to x and with respect to y. It means z is function of x and y. And therefore, first we can differentiate equation 1 with respect to x. We get, to find the root of equation 1 with respect to x, in first we can apply the product formula. First x constant, derivative of log x is 1 upon x plus log x constant, derivative of x is 1. Here to find derivative with respect to x, at that time y is constant term, therefore this term is 0. Z is function of x and y, that we can find derivative of z into log x, again apply the product formula. For z constant, derivative of log of z is 1 upon z into derivative of z is dA by z by dA by x plus log of z constant into derivative of z is log of dA by z by dA by x equal to derivative of constant term is 0. And therefore 1 plus log x plus dA by z by dA by x plus log of z into dA by z by dA by x equal to 0. Then we can transfer this 1 plus log of x in right hand side. From last to we can take dA by z by dA by x as common. Therefore 1 plus log of z into dA by z by dA by x equal to minus in bracket 1 plus log of x. And therefore dA by z by dA by x equal to minus 1 plus log x upon 1 plus log z. Similarly, dA by z by dA by y equal to minus 1 plus log of y upon 1 plus log of z. And therefore, dA by square z by dA by x dA by y equal to dA of dA by x in bracket dA by z by dA by y equal to dA of dA by x in bracket value of dA by z by dA by y is minus 1 plus log of y upon 1 plus log of z. To find derivative with respect to x, at that time y is constant term, and therefore minus in bracket 1 plus log of y is constant term. We can find derivative of simply 1 upon 1 plus log of z with respect to x equal to minus 1 upon 1 plus log of y into derivative of 1 upon 1 plus log of z is minus 1 upon 1 plus log of z bracket square into derivative of 1 plus log of z, in which derivative of 1 is 0 and derivative of log of z is 1 upon z into dA by z by dA by x, and therefore equal to minus minus plus 1 plus log of y into 1 upon 1 plus log of z bracket square into 1 upon z into dA by z by dA by x, and therefore 1 plus log of y upon z into 1 plus log of z bracket square into dA by z by dA by x, and therefore dA by square z by dA by x dA by y equal to 1 plus log of y upon z into 1 plus log of z bracket square into derivative of dA by z by dA by x, nothing, value of dA by z by dA by x is minus 1 plus log of x upon 1 plus log of z. You can substitute here value of dA by z by dA by x as minus in bracket 1 plus log x upon 1 plus log z. Then simplified we get, then we can find the value of this dA by square z by dA by x dA by y at x equal to y equal to z. That way we can put y equal to x and z equal to x. Therefore 1 plus log of x upon x into 1 plus log of x bracket square minus 1 plus log x upon 1 plus log x. Clearly here 1 plus log of x cancel. Here also 1 plus log of x cancel. Remains minus 1 upon x into 1 plus log x equal to minus 1 upon x into. We know that log of e is 1. Therefore replace 1 by log of e plus log of x equal to minus 1 upon x into log of e plus log of x, nothing but log of e into x. Therefore equal to minus in bracket x into log of ex whole bracket raised to minus 1, which is required solution. Thank you. Please like and share this video and subscribe my YouTube channel, Mr. SR Guide. Thank you.